Bismillah Rahman Rahim. Now today is lecture number 10 of the course Hydraulics, and we will continue our discussion regarding rapidly varied flow problems in open channel hydraulics. Now just a recap of what we studied in the previous lecture about the rapidly varied flow. So rapidly varied flow, it occurs when a water flow depth changes abruptly over a very short distance. So this is the definition for rapidly varied flow, that the depth of water, it will change because we have varied flow, clear, non-uniform flow, which we commonly call as varied flow. So the flow depth of the water, that will change abruptly, and it will be over a short distance, clear. So examples of rapidly varied flow that are encountered in open channel hydraulics are many examples. Like we studied about these in the previous lecture. So you can see that if we consider the rapidly varied flow conditions in each of these cases or examples, then it can be, a very detailed topic. So that's why our main discussion regarding the rapidly varied flow problems will be confined to hydraulic jump. That's why you see that in your textbook, so they give the topic is the hydraulic jump, means that this is what we want to discuss when we talk about the rapidly varied flow. So remember, this is just an example of typical example of rapidly varied flow. We can discuss the other example. For example, this one, this flow over spillways, it can be a very detailed topic to discuss the how the flow of water occurs over the spillways and what are the dynamics of that, can be a detailed topic, clear. But anyhow, as per our textbook, we will stick to this hydraulic jump. So as you can see that in these examples, there is significant change in depth, either you see here in this case, or you can see here as the water flows through a bridge. So we have these bridge pairs. So you can see here that the conditions, they change rapidly over short distance. These are all examples of rapidly varied flow, but remember, our main focus will be that of hydraulic jump. Now this hydraulic jump, this occurs when supercritical flow changes suddenly to subcritical flow within a short distance. It is used for dissipating the energy in flow to protect dams, weirs, and other hydraulic structures. I show you the pictures in the last lecture. You saw that in the hydraulic structures, actually this hydraulic jump, it occurs naturally or not. We are not discussing this thing here. We are saying that this hydraulic jump is, you see, the main advantage of this is to dissipate the destructive energy of flow of water. So that's why it is used for dissipating the energy to protect the hydraulic structures. So actually this is desirable. We design the hydraulic structures and then to protect these hydraulic structure against the destructive energy of the flow of water, which you will see in the coming slides. So it is actually desirable that hydraulic jump should occur because this is effective way of dissipating the destructive energy. So this will protect the bed of the channel downstream, and ultimately it will safeguard against any instability that can occur to the hydraulic structure itself, clear. So that's why we encounter actually this hydraulic jump when we talk about the hydraulic structures, clear. Now in this hydraulic jump, whenever the flow changes from supercritical, why supercritical? Because you can see here that this y1, it is less than this critical depth. So this dash line, the red line, it shows the critical depth. because the depth is below the critical depth, so we say this is supercritical depth. Now you can see here that this supercritical depth, it changes to the subcritical depth. Why it need to change to the subcritical depth? This will depend on the flow conditions, because hydraulic jump will not always occur everywhere. This will be the situation whenever the flow changes from supercritical to subcritical. This is the required condition, clear? Because in this case, why the hydraulic jump will occur? You see, the transition from supercritical to subcritical cannot be smooth. As I said before, we cannot say that, okay, very smoothly, this is very smooth line and the depth changes from supercritical to subcritical. This is not possible because it passes through the critical depth. And when the flow passes through the critical depth, we already discussed that at the critical depth, the conditions are critical, and critical means that it is unstable condition, clear? So what will happen is that, if you remember, for critical flow, we discussed that we have this dy by dx, the rate of change of depth that we discussed earlier. So at the critical depth, what is the situation in that case? This was equal to how much? This dy by dx, the equation that we discussed earlier. So this equation basically tells us that what is the depth change. So this depth change that we want to calculate, this is actually equal to S naught minus S, if you remember from the previous lecture. So this is equal to S naught minus S divided by 1 minus F square, where F is the Froude number. So now you know that at critical flow, what is the Froude number? So the Froude number is equal to 1. So now when this is equal to 1, 1 minus 1 square is 0, and anything divided by 0, we actually get infinity from here. So this infinity means that the slope is vertical. This actually points to the slope as vertical, clear? So it means that here the water surface slope, it should be vertical. So that's why, because of this situation, you see that there is a jump and the water surface cannot be smooth here. So that's why it results into this turbulence, which is shown here. This is the turbulence which is created, and we encounter what is known as universally, this is known as hydraulic jump. It means that this phenomena is recognized anywhere. That's why in your book it is written that this is universally known as hydraulic jump. Anywhere this phenomena is called as the hydraulic jump. So this hydraulic jump occurs, you see that in a short distance there is significant change in the depth, clear? When the flow changes from supercritical to subcritical over the short distance, and the changes occur suddenly, abruptly. So that's why this hydraulic jump, this is an example of the rapidly varied flow. So that's why consequently we cannot apply the rapidly varied flow theory here. So now in this lecture we will learn how we will analyze the rapidly varied flow problems that involve this hydraulic jump. Now you can see here, as we discussed, that this is a weir structure shown, a raised structure over which the water flows. So this weir, we discussed, can be used, it is used for as a discharge measuring device, and also it is used to raise the water level upstream, clear? Because it is also used in water management, clear? Not only just to measure the discharge. You will study about this later on in detail in another course, that is irrigation engineering. So we have this hydraulic structure. Now you can see that the flow here is subcritical when the water flows over this structure. Now downstream the depth changes to, for example, here I consider the depth So here the depth is the supercritical depth. Now this depth downstream, the depth has to change to the subcritical condition. This is, you can see here, this is the subcritical condition. And the reason is that why the depth need to change from supercritical to subcritical, because of which this hydraulic jump occur. You can see here turbulence in the water surface, break in the smoothness of the water surface, and this is what we call as the hydraulic jump. Clear? So why this happens? This is the reason is that you see, for example, even on a mild slope, if you remember, we discussed the gradually varied flow profiles. Even when we have a mild slope, on a mild slope, the depth is the normal depth that is greater than the critical depth. Clear? So in this case, let's say we have the hydraulic gate here. This is a gate structure which is used to control the flow of water. So you already know that down upstream here, the depth is subcritical. Downstream, what we are doing here is that this depth here at this point here, it is below the critical depth as well as the normal depth, because this is a mild channel. So in this case, what we have is that this is mild channel. So in a mild channel, the depth should always be more. The depth will be more as compared to the steep slopes, as we already know. So in this case, what will happen, that we are forcing the depth to be supercritical. Because we are forcing the depth here to be supercritical, and as the water flows after this gate, this is actually a gate structure, clear, which we use to control the flow. So because we are forcing the depth here, so what will happen, that this slope is mild, it cannot sustain supercritical flow. It means that the depth will try to be subcritical. So this depth will try to be subcritical on a mild slope. So now what happens is that this supercritical depth, and then this is subcritical depth. So it means this depth will try to come to this depth here, because we have mild slope. Why it come to supercritical? Because we force it to come here due to operation of this gate. So now this depth will again try to become to the subcritical depth, you can say, on a mild slope. So what will happen is that there will be a rise in the water surface. So because there will be a rise in the water surface, clear, and then what will happen is that because it will pass through the critical depth also. So that's why smooth transition is not possible, and it will result into this turbulence, and this is what is known as hydraulic jump here. And in here, before the hydraulic jump, what is this profile here? If you remember, this will be an M3 profile. This will be an M3 profile, which is a rising profile. Clear? This is an M3 profile. And after this, there will be hydraulic jump, and then the water can continue to flow with the subcritical depth on this slope or in this channel. So you see here the same, for example, the water flows over this weir. So this is how you see that we have a supercritical depth here, and then it becomes a subcritical depth here, because it passes through the critical depth. So that's why we encounter this phenomena, what is known as hydraulic jump. Now this hydraulic jump that occurs here because of these conditions. So if we draw the specific energy curve for this hydraulic jump, so you can see here that this depth, this is y1, this depth is y1, that is the depth before the jump. Now if we draw the specific energy diagram, which is very useful concept as what we have learned so far, the specific energy curve that we draw, it's very useful concept in open channel hydraulics, and the reason is that it helps to analyze complex problems. Clear? Now this y1, it is here, so it means that on a specific energy curve we are here. And remember, the discharge is, the flow is steady flow, because in this chapter all the problems that we discussed, the flow is steady, means that with respect to time the flow is not changing. So unsteady flow problem is another, classification of the open channel flows, but unsteady flows we are not going to discuss. Clear? We are only focusing on steady flow. So that's why, remember, the flow is steady in all the cases. Now in this case, the depth is this y1. So we are here, this is now the specific energy. Now after the hydraulic jump, the depth comes here. Clear? So after the hydraulic jump, this depth, it becomes this y2. Now this y1 and y2, they are not for the same specific energy, because for the same specific energy, if this is y1, then for the same specific energy this is y2, but it does not occur here. You see here, this is not here. Where is this depth? This depth does not occur. If this was y2, then these are alternate depths, because we define alternate depths that occur for the same specific energy. So then in that case, y1 is the alternate, because these are the two possible depths. Both cannot occur at the same time, but both are possible. So that's why we say these are alternate depths. Y1 is the alternate depth of y2, and y2 is the alternate depth of y1 if they occur on the same specific energy. But if you see here, in this case, in the hydraulic jump, this is not the case. These does not occur on the same specific energy. What happens is that the depth after the jump is this y2, and for this y2 we have this is the specific energy here. So this is less than, because we are moving towards the zero, we are moving towards the left of this curve. So that's why this curve, as I said, that this is for one specific discharge. If you change the discharge, it will change. For rectangular curve, small q, discharge per unit width, and for other channel, then it will become the total discharge. So we are moving on the same curve, but now it's here. So it means that this y1 and y2, they are not for the same specific energy. And in the last lecture, we learned that this y1 and y2, these are known as this y1 and y2. So these are known as conjugate depths. These are known as conjugate depths. In some books, these are also known as sequent depths or sequent depths. Now you can see here that if y1 is known, we cannot proceed on this vertical line and we cannot calculate y2 directly, as what we have done so far. Clear? Now in this case, as I already said in the previous lecture also, that if we only alone use this specific energy diagram to solve the problem, we cannot. The reason is that this is y1 and then the depth changes to y2. So you can see here there is a loss of energy as a result of this jump. So it means there is a change in specific energy. So there is a loss of energy, and this loss of energy is also unknown to us. How much energy is lost? We don't know. So because we don't know how much energy is lost, if we know how much energy is lost, then it is easy. We can just plot again this second line here, which you see to the left, and then here this will be the required y2. But since we already also don't know that what is the loss of energy in this hydraulic jump. So that's why alone using this figure is not sufficient to solve the problem. That's why we need some additional figure or additional equation that we need in order to calculate this y2, which is the depth downstream of the hydraulic jump. So now in this topic we are going to learn that what additional equation or figure that we can draw in addition to this specific energy diagram that will help us to solve the problem. Now this is the figure which is given in your textbook. So you can see here that we have this supercritical depth, and when this changes to subcritical depth, so there is no smooth transition, and you can see here the turbulence in the water surface, and this is the hydraulic jump. Now in this hydraulic jump which is shown in this, we will discuss it in a simplified way. Clear? That the hydraulic jump is created in a horizontal channel. The bed is horizontal or very small. How much small? We will consider the horizontal bed of channel, but before that let me go through this slide. You can see here, as I already discussed, we have this supercritical flow, and when it changes to subcritical flow, so we have this hydraulic jump. Now in this hydraulic jump, you see here, actually we don't know how much energy is lost, so we cannot directly calculate this y2 from this in a specific energy diagram alone. You see here E2 is less than E1, so it means there is a loss of energy in the hydraulic jump. We will develop an equation how we can calculate. If we can calculate, even here you can see, if we can calculate the specific energies at the two sections, then the difference will give us the loss of energy, clear, as a result of this hydraulic jump. Now you can see here that the depth was here, and now the depth is at 0.2 after the jump. You see that there is a jump in the depth from 1 to 2. This is the jump, hydraulic jump, clear? Now before we discuss the theory related to that, actually what we want to discuss is that in this figure here or shown here, we want to calculate that what is the depth upstream of the jump or what is the depth downstream of the jump. This we want to calculate, because here the problem is alone specific energy we cannot use to solve the problem, clear? And the second thing is that how much energy is dissipated as a result of hydraulic jump, because there are different types of hydraulic jump that we will discuss. So it's not fixed that as a result of hydraulic jump how much energy will be dissipated. That is not constant. So this is what we are going to learn, that how much energy is dissipated, and also we can estimate that what is the length of the jump. For example, it starts from here and then the depth it stops here, this hydraulic jump. So how much is this distance? This we need to discuss. And the location of hydraulic jump. For example, if it is asked a question that for the given conditions, will hydraulic jump occur or not? So if hydraulic jump occurs, then find the location of the hydraulic jump, that at what location it will occur. Clear? So these are the questions that we would like to answer in this lecture, clear, in the coming slides. Now we already discussed some characteristics in the previous lecture, so I quickly repeat them to refresh, because now we are going to develop certain equations. So these characteristics are very important to remember. You know, characteristic features of the rapidly varied flow. Now this is for rapidly varied flow. It is not written here hydraulic jump. It means that these characteristic features we can consider for the different examples of rapidly varied flow. What are those? That number one, curvature of the flow is pronounced so that the pressure distribution cannot be assumed to be hydrostatic. It means that in the hydraulic jump, the curvature is pronounced, and that's why in the hydraulic jump, the pressure distribution cannot be assumed to be hydrostatic. Now, let me come here to this figure which is given in your textbook. You see here that this hydraulic jump, it is shown on a horizontal bed. Why on a horizontal bed? Because we will discuss the theory by simplifying for a simple case, by simplifying the complex problem. Clear? So that we can understand very well and the equations develop are easy to be developed and to be understood. Clear? Now in this case you see here that upstream of this hydraulic jump, you see here the surface, this is the hydraulic jump. So the pressure is hydrostatic. You can see here, so this is the hydrostatic pressure. In here in the flow, we can assume this. Similarly, downstream of the hydraulic jump, this pressure distribution can be considered as hydrostatic. This is what we are commonly doing when we discuss the problems. Clear? Now, this pressure distribution diagram here I cannot show. In the hydraulic jump, you see we have turbulence. So here if you show this hydrostatic pressure distribution diagram, so this is not correct. This is what it says. This one is fine, just upstream of the jump. And just downstream of the jump, it is fine that we consider this hydrostatic pressure distribution diagram, but inside, because there is abrupt change in the depth and turbulence, you can see here. So we cannot assume here that the pressure distribution is hydrostatic. Clear? The second thing is that the rapid variation occurs over a relatively short distance so that boundary friction is comparatively small and usually insignificant. So what we do is that when we do the analysis, so then in that case, this occurs because the conditions change abruptly and over a short distance. This distance between this section 1 and this section 2, this distance is very small. Clear? So because this distance is very small, that's why the friction forces along the boundary of the channel that are insignificant. We cannot say zero, but these are insignificant. And in the analysis, we can, these are negligible and we can ignore this without much error in our calculations. Clear? So that's why the friction forces which we use to consider here at the boundary of the channels. So this, in case of the analysis of rapidly varied flow, we will neglect these friction forces. The reason is that we have short distance. When the hydraulic jump occur, it is over a short distance. So that's why the friction, it can be neglected. So this you will see. Now we will discuss the theory, we will develop the equation. So you will see we will apply these characteristic features. And rapid changes of water area occur in rapidly varied flow, causing velocity distribution coefficients alpha and beta to be much greater because we have turbulence. So that's why the rapid changes occur in the area, in the water area, when we have rapidly varied flow. So that's why these coefficients, which we are commonly assuming as unity 1 in the analysis, whether we have pipe flow or we have open channel flow. If you remember, alpha 1 means the kinetic energy correction factor at section 1 and at section 2. So far commonly we are assuming them equal to 1 and we solve the problems. This was the case also in fluid mechanics too. We study the pipe flow problems. Same there, we also consider these as equal to 1. And so far in this chapter also equal to 1. But when we discuss a rapidly varied flow problem, so this assumption no longer holds. So in rapidly varied flow problem, this cannot be assumed as equal to 1 because it is written here much greater than unity. So that's why in the analysis we have to consider them. And not only this, alpha is actually what? This is the kinetic energy correction factor. So this is alpha v square divided by 2g. So because we have non-uniform distribution of velocity, if we have uniform velocity everywhere, then no need of this correction. But as we studied in pipe flow also, velocity profiles in fluid mechanics too, but also in the beginning of this chapter in open channel flows, that there is non-uniform velocity distribution. So that's why we need to apply this correction so that the value calculated by this is approximately or very near to the true value. Clear? And this is not only for this, we also have this beta, which is the momentum correction factor. Clear? This is beta 1 and equal to beta 2, and this we are so far assuming equal to 1, but in this case cannot equal to 1. This beta, actually we did not apply the momentum equation yet, now we will apply. But this, if you remember in fluid mechanics 2, momentum and forces in fluid flow, this summation of F is equal to what? Rate of change of momentum. So this is rho q, the mass flow rate, into the change of velocity. So because again we have the velocity, so that's why in here you need to multiply beta here. We need to multiply beta here. This is the momentum correction factor because the velocity is non-uniformly distributed. So because it was equal to v2 minus v1, if you remember the change of velocity, so that's why accordingly it will be equal to beta 2 times v2 and beta 1 momentum correction factor times v1. But we commonly assume them as equal to unity. So this momentum correction factor and the kinetic energy correction factor, then in the rapidly varied flow problems, so because the change conditions are changing rapidly, so we should not assume them as equal to unity. Now you will see that these assumptions now we will try to apply when we develop the equations for the hydraulic jump. Clear? So now this is the figure which is given in your textbook. Now let us try to discuss the theory of the hydraulic jump. Now in this case, this is the hydraulic jump which occurs downstream of this spillway. The water flows over the spillway, and because downstream here we have the supercritical depth, this y1, and it changes to y2, which is subcritical depth. So it passes through the critical depth, the flow depth passes through the critical depth. As a result, we have this hydraulic jump. Now we have this y1, and because the water is flowing with very high velocity v1, you can compare. You see here the scale. This is the y1, and you see here v1 square by 2g. See the scale. It means that the water is flowing with very high velocity. And this is the energy line. So we have the depth of flow plus the velocity head. So you have the total energy at this point here. Now when the water flows, so you can see here at section 2, we have the depth is y2, and because the depth has increased, the velocity will decrease. Clear? So you can compare here, this is y2 here, and you can see here this is y v1 or v2 square by 2g. This is the velocity head. So what happens is that you can see that y1 plus v1 square by 2g is the energy here, which is E1. Let us assume this is equal to E1. Clear? And in here, this depth of flow plus v square by 2g, so the velocity here is E2. Specific energy E2. Now you can see that there is a change in the specific energy. So it means that the specific energy has decreased as the water flows from section 1 to 2. So whenever there is a decrease in the energy, where the energy goes? This energy will be lost as a result of this hydraulic jump. So there is a decrease in energy, and this is known as the head loss. Clear? Now this head loss in here, this is not due to the friction forces, because we already discussed in the characteristics of rapid vary flow that the changes occur over a short distance, so the friction is small and usually insignificant. Now in here, we are not considering the friction forces. So you can ask a question that if there is no friction, how come the head loss occur? So this head loss, this occur due to, you see here, decrease in the specific energy. Because the energy has decreased, so that energy is lost. And this is what we say, it is HL. Now this distance between the two sections is very small, so the friction forces are negligible because of the short length of channel involved. Clear? So that's why friction forces we will not consider here. So this head loss, this is due to decrease in the specific energy. As I said before, in case of uniform flow, where the depth is the same at all sections, then the specific energy remains constant in uniform flow. This is non-uniform flow, varied flow, so that's why the specific energy can increase or decrease. Clear? If we consider a general case where the flow occurs in a channel and there is friction forces. So remember, the energy, it will always decrease in the direction of flow because of the friction. This is what we learned so far. There will always, the total energy, it will always decrease in the direction of flow, the total energy. We studied that in case of uniform flow, in uniform flow, the definition is that the depth is the same at all sections. So we are assuming the depth to be the same at all sections. That's why the specific energy line, if we do not consider any other energy, if we do not consider the head loss, then you will see that the energy line, it will be horizontal because the depth is the same at all sections, the velocity will be the same at all sections. So the specific energy that we discuss, that will be constant. Clear? Then we studied that in case of varied flow, uniform flow, it is constant. In case of varied flow, then what happen is that, this is what we discuss, that either the surface can rise in the direction of flow, or it is also possible that the surface can decrease in the direction of flow, the drawdown curve. You remember the drawdown curve, and this is the backwater curve. So then in this case, you see the specific energy is not constant. So it can increase or it can decrease, clear, depending on the given condition. So that's why you can ask a question that now here we neglect the head, this friction forces. So now if there are no friction forces, why we say that this is a head loss? This is a head loss because you can compare E1 is greater than E2. So this is what? This is energy. Now the energy at 2 is less than the energy at 1. So it means that when the water has, the water continues to flow from this section 1 to 2, there has been decrease in the energy. So that energy is actually lost as a result of this hydraulic jump. So this is what we say as HL. And this HL is simply E1 minus E2. If we can calculate the specific energy at the two sections, then the difference will simply give us the value for the head loss. So this was a little confusion I wanted to clear. because it was asked a question that we do not have the friction forces, so how we say that this is the head loss. Clear? Another thing is that in your textbook we are discussing the hydraulic jump for a simplified case. Simplified case means that this hydraulic jump occurs on a horizontal bed. So it means that the slope of the channel is very small. And how much is the small? So the theta that we consider as the slope of the bed of the channel, the theta, let's say this is theta. So this will be actually less than, not equal to E1. It is given in your textbook, less than 3 degree. So for this simplified case, we are considering this. And what will be the advantage for this in the analysis is that this theta is less than 3 degree. This is what we consider 3 degree, or if you take tangent of this, so it means that S naught is equal to 0.05. This is tan 3 degree if you take, so this is approximately S naught is equal to 0.05. Why we consider the channel, if in this analysis or derivation the channel to be having a gradual slope that is less than 3 degree or S naught is equal to 0.05, the gravity component of the weight is relatively small and can be neglected without introducing significant error. It means that you see we have the weight of the fluid between section 1 and 2, and commonly if you remember we consider weight of the fluid. So the gravity component of the weight is then small and it can be neglected, because if you remember what we have done even in the pipe flow as well as in the open channel flow, when we have this flow occurs, this is, let's say, bed of the channel. When we consider the two sections, that let's say, okay, this is section 1 and this is section 2, if you remember we consider the weight of the fluid, so which is acting down, and this was the weight of the fluid, and then this is the component which causes the flow, the gravity component. We can complete this triangle. So this component we can neglect now. If you remember earlier, we consider this component of the gravity component of the weight. So then when we consider horizontal bed of the channel, then this gravity component of the weight, it can be neglected. Clear? So we are discussing very simplified analysis for the hydraulic jump now. But remember, if this hydraulic jump occurs on a steep slope, then you have to consider this gravity component of the weight. Otherwise, the results will not be accurate. Clear? So it means for the hydraulic jump, we are considering very simplified case. Remember, upstream of the jump, we can consider this hydrostatic pressure distribution diagram upstream of the jump. And downstream of the jump, we can consider this hydrostatic pressure distribution diagram, but not in the hydraulic jump here because we have turbulence. Now in this case, the friction forces we neglect because the length is short, and because it is on a horizontal bed, the theta is very small. We also neglect the weight component. So now the only significant forces are the hydrostatic forces. We have this force here, the hydrostatic force, let's say F1, and this force here, let's say F2. Only these two forces now we can consider. These are now the significant forces. The friction forces are neglected because of the short length, and also the gravity component of the weight, that it can also be neglected because we have horizontal bed. So now with this, now let us try to develop the equations. So first we discuss for a general case that will be applicable to any shape of cross section, and then our main focus will be that on rectangular channels, because for rectangular channel the equations are easy to develop and understand. That's why we always focus on rectangular channels. Clear? So now in this case, what we do is that we will apply the momentum equation. This is the momentum equation, as we discussed that this is also very fundamental equation in fluid mechanics. So this momentum equation we will apply now to solve the problem. And what it says that summation of forces, this is equal to, now it is in x direction, so you can put a subscript x in this direction, that is equal to the rate of change of momentum. This is the rate of change of momentum in fluid flows, rho q delta v. We developed this equation, derived this equation in fluid mechanics 2 course, so you already know from there this rho q is the mass flow rate and this is the change of velocity. Now we apply the momentum principle to the fluid between this section 1, this is section 1, and we have this section 2 here. And remember, now it is general. Later on we will make it to applicable to rectangular channel also, but this is general. General means that this equation that now we are going to develop, it will be applicable to any shape of cross section, rectangular, non-rectangular. Clear? So now let us start with this. What we have is summation of forces. Now we apply the momentum equation, summation of forces, let's say in the x direction. So this will be equal to what? The two forces we have here, F1 and F2, the hydrostatic forces. So because they are acting in opposite direction, so plus minus sign. So what are these forces? Let me directly write down F1. So this F1, this will be equal to gamma into HC1. HC is the depth of the centroid of the area for a section 1, and we have area A1. This is actually your F1. You already studied this in fluid mechanics 2 also, and also the pressure chapter in fluid mechanics 1. So it is coming from there. Gamma is the specific weight of the fluid, and this minus gamma HC 2 into area A2. So these are the summation of forces. The two forces now significant, we neglect the other forces, and this must be equal to the rate of change of momentum. So this must be equal to rho q into V2 minus V1. So let's say this is equation number 1. This rho can be written as gamma by G, because we already know that this rho is equal to gamma by G. So we need to write down this gamma by G, because gamma is written on the left hand side also. We can then later on cancel it out. So let us simplify this. This will be equal to gamma by G, because we have the same fluid. So that's why we can then cancel out this to simplify our equation, gamma by G. Now this HC is the depth to the centroid of the area. Clear? HC is the depth to the centroid of the area. Now we rearrange this equation. So now rearranging this equation number 1. So we get this as gamma divided by G into Q V1 plus gamma HC1 into area A1. This will be equal to gamma by G Q into V2 plus gamma HC2 into area A2. Let's say this is equation number 2. Now in this equation number 2, it states that the momentum plus the pressure force on the cross-sectional area is constant. What is this first term here? This is coming from this momentum on the right hand side, and what is on the left hand side we have, this is the pressure force. Actually what we have this pressure that is equal to force by area. So P is equal to force by area. Now you already studied that for hydrostatic pressure is P is equal to gamma times the depth, gamma into H. So you can see here force will be equal to P times A. So that's why force will be equal to gamma H into A. So this is actually the pressure force. So we have the momentum plus the pressure force on the cross-sectional area is constant. This is what this equation 2 states. It is like you write down P1 by gamma plus Z1 plus V1 square by 2G is equal to P2 by gamma plus Z2 plus V2 square by 2G. You remember from Bernoulli equation? So this is actually like that the momentum plus the pressure force, it is constant. Clear? This states that the momentum plus the pressure force on the cross-sectional area is constant. So consequently, you see that as we have continuity, so Q is equal to A1 V1 is equal to A2 V2 and also gamma is present on both sides. So what you can do is that divided by gamma. That's why we write down in terms of gamma. So what we get, this equation here, that this will be equal to Q square. Now you simplify this will be equal to Q square divided by AG, A times G plus area A into the depth of centroid. This is equal to constant. Let's say this is equation number 3. So now this equation, it applies to any shape of cross section, because now we are discussing generally. It applies to any shape of cross section. Now this quantity here, which we have, the first term, that is Q square divided by AG. So this first term is actually what? This is momentum of flow passing through channel section per unit time per unit weight of water. How this is the case? You can see here that if I write down, let me just explain this. This is actually, I just explained for you. This term is the momentum of flow passing through channel section per unit time per unit weight of water. You see in the above here we write down rho Q delta V. This is for understanding. Now we have rho Q delta V. We studied this is the rate of change of momentum. This is the rate of change of momentum. Now we already know that V is equal to Q by A. So this term which is written here, this can be written as rho Q into Q by A. Let me write down this like this. For section 1 and 2 we can do it. So this is equal to Q by A. Clear? So now this will be equal to rho q square by A, rho q square divided by area A, and this rho q square by A, it can be written as gamma by G. It can be written as gamma q square divided by G into area A. Clear? Rate of change of momentum. And then if you divide this by weight, if I divide this by weight, so this gamma and gamma cancel out, and what we are left? We are left with q square divided by G and A. This is what we get here. So this is essentially momentum of the flowing water through the channel section per unit time per unit weight of water. So this is actually momentum, if we can write down in words. So this is momentum per unit time per unit weight, clear, into weight. Per unit weight. Weight of what? Weight of water, the liquid that we consider. So this is essentially, these are essentially force per unit weight of water, clear? And this term here, A into HC, this A into HC, this is what? This is force per unit weight of water. This is force per unit weight of water. Why? Because you have this force. What is the force? So the force is gamma HC into A. So force is gamma HC into A. Now you divide this by gamma. What do you get? This HC into A. So this is force per unit weight of water. So it means that both these terms are essentially force per unit weight of water. So that's why their sum is known as, this is denoted by Fm in your textbook. This is denoted by capital Fm, and this is known as specific force. This is given the name as specific force. This is known as specific force, clear? So this is important concept in this. We are discussing the theory of the hydraulic jump. This is very important concept, clear? So this is now applicable to any shape of cross section. Now, essentially these two terms, these are force per unit weight of water. That's why this is the sum of these two components. This is known as specific force. So remember, this is now, we are coming to very important concept. This is known as the specific force. This is now for general. Now let us try to make it applicable for this rectangular channel by simplification. So what we do is that for a rectangular channel, now we consider the rectangular channel, this HC, the depth of centroid, so that is equal to y by 2, half of the depth, clear? Because we have rectangular flow area. So this is your rectangular flow area. So you already know that if this is y, so now where is the centroid for this area? Half from the top or from the bottom? It is half. So this will be equal to y by 2. This is centroid of the area, clear? Now we are simplifying for rectangular channel, see. So this is equal to y by 2, and the area, because we have rectangular channel, so this will be equal to b times the width of the channel into the depth of flow. And also we know that the total discharge, that will be equal to width multiplied by the discharge per unit width, if you remember. So q is equal to, small q is equal to capital Q by b. Now for unit width, because we go for unit width to simplify the equation, so for unit width, so for unit width, what we have is that when you simplify this equation, this capital F now becomes small f. This capital F, which is applicable to any shape of cross section, for the total discharge. Now in rectangular channel we go for the unit width. Clear? This is the unit width, so it becomes a small f. So this is equal to Fm, and this is equal to Q square, is equal to Q square now divided by Gy1 plus y1 square divided by 2, and this is equal to Q square divided by G times y2 plus y2 square divided by 2 . This is constant. This is what we have written here now for unit width. So this is constant. Clear? Now by plotting the depth against the specific force for a given channel section and discharge, we will obtain a curve that is known as the specific force curve. Let me go to now this one figure here. So you can see here, this is the same as the depth, and for the depth versus the specific energy, when we plot it, we get the specific energy curve. Now we have the equation for the specific force, and if we plot the depth versus the specific force, this is now for a rectangular channel, remember. So we get a curve. This is known as specific force curve. So that is specific energy curve, and this will be known as specific. This is very useful concept. Specific force curve. Now this specific force curve, clear, it looks very similar to the specific energy curve, but it is totally different concept. It is totally different concept, clear? Now for a given, we said that the specific force before the jump and after the jump is the same. This is what we are writing here. What we have written here, that this specific force, this is for a rectangular channel, it is the same. You see, the sum of the two quantities is the same before and after the jump. It is constant. So that's why if I come back to this figure here, you see that for the same specific force, clear, for the given value of the specific force, the curve has two possible depths, y1 and y2. You can see here, this is y1, and this is y2 for the same specific force. And these are known as conjugate depths or sequent depths, because you see here it gives the depth before the jump and then it gives the depth after the jump. So I will come back to this again. Let us now continue discuss with this. Now, for a given flow rate in a rectangular channel, the minimum value of the specific force occurs at the same depth as the minimum value of the specific energy. You can see here, this is the minimum value of the specific force, because if you move on the curve on either side, the value increases. So this minimum value of the specific force, here we will have yc, and for this minimum value of the specific energy, we also have yc. If I go proceed and cut here, this is also yc. So we want to know that the minimum value of the specific force occur at the same yc as the minimum value of the specific energy or not. Let us see what condition we get. So for this, what we do is that we will differentiate this equation. So what we do is that we differentiate this specific force equation. Differentiate this Fm with respect to y. And equate to 0. And equate to 0. So what we will get here, this d by dy of this Fm, that will be equal to, actually what we have, you have this Fm and this is equal to q square. Now we can write down here in general term q square divided by gy plus y square by 2. This is now the equation. Let us drop this y, this 1 and 2. Discharge is the same. So now when you differentiate this equation, now you differentiate here. So what we will get? We will get minus q square divided by gy square. You take the derivative, it will be gy square plus 2y divided by 2 equal to 0. Now you simplify this, what you will get from here? You will get from here is that q square, that is equal to g into y cube. You see this 2 will cancel out, this y can come to the other side and then multiply with y square. So this will be equal to q square is equal to gy cube. And now from here what we get is that this y, this is equal to q square divided by g into whole power 1 by 3. Now which is the condition for critical flow? You see, this was what the condition in case of rectangular channel. This was condition for critical flow. This is what we developed earlier. This was the condition for critical flow. So now what it means? It means that for the given q, small q, for the given discharge, the minimum value of Fm, the specific force, occurs at the same depth as does the minimum value of E. It means that what we discuss here, that the minimum value of Fm will occur at the same depth as does the minimum value of the specific energy. So now it means that for the critical flow, we have the critical depth, the discharge was maximum from the discharge curve. You remember the discharge was maximum, the specific energy minimum, and now add another condition, that for the critical flow, for the critical condition, the specific force will be minimum. This is now what we prove here. Clear? Now to continue with this, as we already have this equation above, which is written here, this equation that we have written here, what we can do here is that this q square divided by g y1 plus y1 square by 2, this now we want to simplify this equation. At the two section, we want to now simplify this equation. So now simplifying, what you will get? We will get as equal to q square divided by g into 1 divided by y1 minus 1 divided by y2. This will be equal to half into y2 square minus y1 square. Let's just simplify this equation. Clear? Now we continue with this simplification. So this will be equal to q square divided by g into y2 minus y1. We just need to now solve. This is equal to y1 into y2 divided by 2 into y2 square minus y1 square. Now we continue with this. So this will be further equal to q square. You can do the calculations, the math. So q square divided by g, this will be equal to y1 y2 into y1 plus y2 divided by 2. Just simplify now. I'm just simplifying the equations. Now you see, before we continue with this, you see that we have q square. This is q square divided by g. This is what is written here, q square divided by g, that is also equal to yc cube. That is also equal to yc cube. You remember? So this q square by g is equal to yc cube, and this q square by g is equal to this, where this y1 is the depth upstream of the jump, and this y2 here, that is the depth downstream of the jump. So what does it mean? It means that if for example, we can write down, if y1 is less than yc, if y1 is less than yc, then it is must then y2 must be greater than yc. So this proves that the hydraulic jump must always cross the critical depth. It must cross the critical depth. Okay, now let us continue with this. As we already know, let me further simplify with this. As we know that the discharge is the same due to the continuity rectangular channel. Remember, we are working for rectangular channel. This is important. So small q, that is equal to V1 into Y1, is equal to V2 into Y2. So now with this equation, now I can write down this equation above one. This I can write down Y1 square V1 square divided by G, that is equal to Y1 into Y2 divided by 2 into Y1 plus Y2. Now this can be further simplified. This will be equal to Y1 into V1 square divided by G, that is equal to Y2 by 2 into Y1 plus Y2. Clear? Now this can be further classified. Just continue with simplification. So this will be equal to 2V1 square divided by GY1 into equal to Y2 by Y1 into 1 plus Y2 by Y1, Y2 divided by Y1 here. This is Y1. Now Froude number, we define the Froude number, that will be equal to, for section 1 now we are working, so that will be equal to V1 divided by square root of G into Y1. So now this equation that we have written here, this equation, this can be written as 2F1 square is equal to Y2 by Y1 says Y2 by Y1 plus this will be equal to Y2 by Y1, this is whole square. Now this equation can be written as Y2 by Y1 whole square plus Y2 by Y1 minus 2F1 square equal to 0. This is now quadratic equation. Clear? We need to find the roots of this equation now. We can apply the quadratic formula you can apply. For example, we already know that we have ax square plus we have bx plus c equal to 0. So now in this case, when you solve, clear, solving, So what we have x, these are the roots now, that will be equal to minus b plus minus square root of b square minus 4ac divided by 2a. So like this we can apply this quadratic formula, clear? And we will neglect the negative sign. So just this is now the quadratic equation that we need to solve using this equation. So just you need to calculate what is a. A is the coefficient of the x square, so here a is 1. B is the coefficient of this x here, so b is again 1, clear? And this coefficient here plus c, so it is given by this equation here. So just when you put the values, we will get y2 is equal to y1 divided by 2 into minus 1, clear? This is equal to minus 1 plus, we will only consider the plus, so plus into 1 plus 8 f1 square, fruit number at section 1, either like this, or if you put the value for the fruit number, it can be also written as y2 is equal to y1 by 2 into minus 1 plus square root of 1 plus 8 q square divided by g y1 cube. This is y1 cube. So this equation here, let's say equation A, above or below, whatever you write down, this one or this one. So this is, you can see if y1 is given, if the depth before the jump is given, you can calculate the depth after the jump. This equation you can use. So alternatively, what we did, we can also develop the similar equation for y1 if y2 is given. So I will just simply write down that. You can proceed like what we have done so far. So alternatively, what we can look to this problem is that now we will consider q is equal to v2 into y2. First we consider v1 into y1. Now we consider this, and also we will consider the fruit number at section 2, and this will be equal to the velocity v2 divided by square root of g into y2. And when you simplify like what we did for obtaining equation A, then we will get this y1 now will be equal to y2 divided by 2 into minus 1 plus square root of 1 plus 8 now f2 square, either this one or this can be written as y1 equal to y2 divided by 2 into minus 1 plus square root of 1 plus 8 q square, discharge is constant, divided by gy2 cube. This is now gy2 cube, and this is equation B. So remember this equation A and B relate the depths before and after the hydraulic jump, and these are known as conjugate depths. And remember, these are for rectangular channel. So this is important. These are for the rectangular channels. If we go deep into that, so hydraulic jump in non-rectangular channel, that can be another discussion. But these are limited to the rectangular channel as per our textbook. And remember, these equations that we calculate the depth before and after the jump. If the depth before is given, we can calculate the depth after the jump. If the depth after the jump is given, we can calculate the depth of water before the hydraulic jump. These equations give good results when the channel slope is about 0.05 or less than 3 degree. This is what we write down. Remember, for steeper channel slopes, the effect of the gravity component of the weight of the liquid between the two sections must be considered. If we have steeper channel slopes, then these equations will not give you good results. So you have to consider in the analysis the gravity component, clear, of the weight of the liquid between the two sections. So we take a break now and we will continue after the break.